have on your shoulder? Ball and socket joint. Let me see, can your ball and socket joint spin in the X? So let me go in the same way. Can it spin in the X? Can it spin in the Y? Can it spin in the Z? And I can make it pretty wide if I want, right? Santiago, stand up. Can he pull my arm out of the socket?
He could.
Maybe if it was really strong, but my ball and socket should be resisting it, right?
Yeah, should.
Okay, how about in the X direction? Can it resist it? Yes. How about in the Z direction? Can it resist it? Yes. Thank you. So, a ball and socket joint, can it resist a force in the X? Force in the Y? Can it resist a force in the Z?
Yes.
Yes. Can it resist a motion in the X?
Yes.
No, because it spins, right? It's not resisting it. Look, Jack can take my arm and just swing it all around whatever way he wants, and I'm like the rag doll, right? I'm not resisting it at all. It's free motion. So rather than using the word resist, let's use a different word. Let's say free to move. So can my arm free to move rotation in the X? Yes. Rotation in the Y? Rotation in the Z? Yes, it's free. But is it free to move translationally in the X? No, it's not free to move in that direction. Free to move in the Z? No. Free to move in the Y? No. So in the end, this kind of connection, a ball and socket joint, can resist how many motions? Linear motion. And how many directions? 3. So let's back up a little bit. So for 2D, tell me what the possible motions are. Possible motions. Okay, X and Y, but X and Y isn't telling me enough. You have to tell me the type of motion. Translational in the X. What else? Translational in the Y. And it's a 2D problem.
Rotation the next one.
No? Come on, you guys. A 2D problem, so don't think about the ball and socket joint right now. Forget about that.
That's not.
What did we learn before? In a two-dimensional problem,
Compression.
no, not, well, it could be compression or tension or whatever, but that's translational. So in a two-dimensional problem, it has the ability to move up and down. That's one linear translational motion. It has the ability to move side to side. And what's the third thing that it could do? Rotate about Z. You know that.
Of course.
Of course. So for a two-dimensional problem, the possible motions it could have is for 2D, it could move translationally or linearly in the X, it could move linearly in the Y, or it could rotate about the Z. Everybody comfortable with that? Two-dimensional problem? Let's do 3D now. Let's draw our axes again. Okay, so for 3D, what's the possible motion that could happen in the X? I could have translational in the X. Let's continue with translational. Can I possibly have translational in the Y?
Yes.
Yeah, I can move up and down. How about in the Z? Can it move forward and back? How about rotational in a three-dimensional problem? Can it rotate about the x-axis?
Yes.
Yeah. It could rotate about the x. How about the y?
Yes.
It could rotate about the y. And in the z, can it rotate?
Yes.
It could rotate about the z. So in a two-dimensional problem, what's the maximum amount of motions it could have? 3. 3 possibilities. And for 3D, we have 6 possibilities. So what are some questions about this? Everything as engineers we design is really in the end a 3D problem, right? But why do we analyze it as 2D sometimes? To simplify it, right? So there are times that we analyze things as 2 dimensions because it's easier to simplify it. Okay, so let's go back to the ball and socket joint. In the ball and socket joint, 2D or 3D, we're using our shoulder. It's 3D. So what are the possible motions that could occur in a ball and socket joint as 3D? 6, and what are they?
All the
Okay,
translational.
translational in the X, translational in the Y, translational in the Z, and what else?
Rotational, the X, Y, and Z.
Rotational in the X, in the Y, and the Z. Does everybody agree with that? Those are the possible motions. But we just looked at a ball and socket joint, right? And what did we realize are indeed the motions that it has? It just has the rotational. It's free to move here. It's free to rotate about the X. It's free to rotate about the Y. And it's free to rotate about the Z. And what did we learn about the translational? It resists it. So it's not free to move. It resists. And let's say, to simplify it, rather than writing down translational, it can resist a force in the X. It could resist a force in the Y, and it could resist a force in the Z. Questions so far? So if Santiago came up and grabbed my arm and started swinging it around, a rotation, forever and ever and ever, is my arm going to break? It won't break unless he does what?
Yanks it.
Pulls it in one of the directions, right? My arm is free to move rotation in all 3 directions. My arm is not going to break if you rotate it. But shoulder, sorry. But my shoulder could break if it is subjected to too much of a force in the X, Y, or Z, right? Because that's the thing that it resists. It resists these forces, so that means that this is where failure can occur. There is no, or let's say, no failure can occur due to rotation. Okay, so everybody got a table. Let's take a look at that table. just gonna put it up here. Let's look at ball and socket joint. So let's read what the table says. So all these things are called connections. They're also called supports. They're the same. They're synonyms. Connections and supports, they're synonyms. It says for each connection or support, whether they're considered 2D or 3D, and we're gonna see sketches of each one of them. Then on the top, it says, what are the reactions at support? So we don't really, I haven't introduced what that term means. But what that term means, it means what forces or moments it can resist. Everybody hear that? So reactions at supports are the forces and the moments that it can resist. So let's go down to the ball and socket joint, which we've done. Right, we demonstrated it with something that we know and we use all the time, shoulder. Can a ball and socket joint resist a force in the X? Yes. Can it resist a force in the Y?
Yes.
Yes. Can it resist a force in the Z?
Yes.
Yes. Can it resist a moment?
No.
No. Can it resist a moment in the Y?
No.
No. Can it resist a moment in the Z?
No.
No. Is everybody comfortable with what we're doing? So what does the term reaction at support mean? It's the force of the moment that it can resist that in the end can break the connection. Right? Okay, let's do another one that we're very comfortable with. And if you have your textbook, we could look at a picture of it because we want to make sure that we're using the same axes. So let's look, if you have your textbook, you can look on page, if you have your textbook, you turn to page 233. If you don't have your textbook, turn to the packet. And probably everybody has the packet, so maybe let's look at the packet instead. So in the packet, on page 22. So this is what it looks like. And we're looking at a hinge. Is it on page 22? Yeah?
There.
Okay. So you can look at this if you want, but I prefer to actually look at the real thing, a hinge. To the back. No, that way. All the way. Great. Okay, so there are hinges in here in the wall. For the door, next to the frame. Everybody look over here. Here's the door connects to the frame of the frame. So what do we want to call X? Let's do the moments first. So if we let's call the XY plane the horizontal plane, and let's call Z going up. So when I open this door, what is it rotating on? Which axis? Z. So everybody agree we're calling this Z? So is it free to move in this a moment in the Z?
Yeah.
Yeah. Does that mean, does it resist a moment in the Z? No. How about a moment in the X? Can I take the door and spin it about the X-axis? No. Can I take it and spin it about the Y-axis? No. So it can resist it, right? So let's fill in our table for a hinge, which is also considered a 3D. Here's my hinge. Can it resist a moment in the X?
Yes.
Yes. Moment in the X. Can it resist a moment in the Y?
Yes.
Yes. Moment in the Y. Can it resist a moment in the Z? Remember, the Z is the one that the axis that's going up vertical. It could spin about that, so there's no.
Well, I guess it just depends which axis it's rotating about.
Right, it depends on the axis, so that's why we had to choose the axis first, right? So if we look at this, let's see what axis they chose for the hinge. Well, the hinge is a different one,
I
right?
chose X.
They
yeah.
chose X, they
Or
chose
Y.
Y, right? They chose that it's rotating about the Y. So it really depends on what your axes are, and from the beginning, I've been saying, you know, when you draw a free body diagram, you could draw whatever axis you want, and it depends on what axis you draw as to what you're communicating to me. So in this particular case, it's allowed to rotate about, does everybody agree that it's allowed to rotate about the Y-axis, right? So it can't resist that, right? So it's not drawn, it's not a reaction to support. Rachel, you had a question?
Would you like to ask about the table about like using the axes? in
You could
the-
choose whichever axis, so what probably would be a good idea is for you to draw a little sketch here.
Okay, can we just do all of them relative to the?
Yeah, you could do them all relative to what's on the packet, that's totally fine. So should we change it then? What would you like to do? Should we do it all relative to the packet?
Yeah.
Yeah, okay, so let's change it then. So relative to axes in packet. Okay, so then which one should we know then? Moment in the Y, right? And there should be a moment in the Z. How about the forces?
They're all resistant.
Say it again?
They're all resistant?
They're all resistant, right? I can't take this, you know, if I took this door and tried to pull it in the X, Y, or Z, it's resisting it, right? But if I pull it too hard, or I use a crane or something to pull it, well then in that case, I'm actually gonna fail it, I'm gonna break it. So if it's resisting, what do I need to write in the table? Fx, Fy, and Fz. So what do reactions at supports mean? What do reactions at supports mean? What?
Could cause a break.
It could cause a failure, and it resists that motion, right? The goal of a hinge is to resist all the forces in three directions. The goal of my shoulder is to resist the forces in all three directions, right? But it's not supposed to resist any kind of motion. So a reaction and a support is the force or moment that it resists, it's trying to resist to be a successful connection. And if it doesn't resist them, then it winds up breaking. So let's go back to the 2D and 3D. We said that